Fantastic. So today we have James Day, who's a research associate and senior scientist at the Blueson Matter Institute at the University of British Columbia. His work spans condensed matter physics, physics education research, and the intersection of science and the arts. He co-developed the Concise Data Processing Assessment tool to better understand and support students' skills with measurement, uncertainty, and data analysis in intro labs. And on a personal note, James and I go back decades now,
Way, way, way.
way back. We were graduate students together. So, welcome, James.
Thanks, Chris. And thanks everyone for having me. I I gather this is rather casual and informal, so I'll encourage folks to stop me if they want to ask a question or have a little conversation. That's totally fine. Um, okay, so Chris read my bio, but I thought I'd let you know a little more about who I am and where I'm coming from, just so you've got better context in your head about the work I've done and what I'm choosing to present today. So I would say that I'm an experimental researcher by trade. I went to grad school with Chris. I studied solid helium. That low temperature physics experience landed me a postdoc at the Department of Physics and Astronomy at UBC back in 2008. I joined a group then that mostly did microwave spectroscopy, and that's when I really got started in first year labs in particular, when I started teaching at the university level. And we'll talk a little more about that. Um, and I managed to stick around. I came to UBC thinking I'd only be here for a couple of years as a postdoc before going on to the next, but we had just started a family and I liked living here way too much. And I did what I could to stick around. So I now support a group that primarily does scanning tunneling microscopy. I'm an instructor by choice, so contractually, I'm only expected to do research, but I'm occasionally asked to teach. I'm allowed to ask if I can teach, and I certainly do that now and then. So when I started my postdoc for the first, um, actually maybe for the first 4 or 5 years that I was at UBC, I was very heavily involved in the first year undergrad labs. I've taught a couple of grad courses to do with PER methods. And actually, just this last semester, I taught a second year physics undergrad course, mostly dealing with electronics and circuits. We had students build an AM radio. And so, because contractually I'm a condensed matter physicist, I would say I'm a periodic visitor to the PER world since I started my postdoc. A lot of it's off the side of my desk when I'm interested in doing it, and when I have the capacity for it. So sometimes I'm more involved and up to date with stuff that folks are doing, and then I might go a couple of years a little out of it. And then Chris mentioned this. It doesn't really. I'm not really covering any of this in my talk at all, but I I love the intersection and interaction of art and science. I do a lot of stuff here at the Quantum Matter Institute, bringing artists in and trying to nurture some interesting relationships. Anyway, so that's who I am. Chris mentioned that I'm here in part because we know each other. I gather that you folks had a conversation early in the year talking about assessments, and maybe someone mentioned the CDPA, and Chris said, I know that dude. We can ask him to see if he can come talk about it. So that's one reason why I'm here, but I'll let you know up front, and I'll come back to this in a later slide because I've just been a periodic visitor to the PER world. I actually haven't really thought about the CDPA very much in the last almost decade. So when I started putting slides together, I didn't want to just like present a paper. And so I've sort of ended up with slides that are part retrospective, part methods piece, because I think there's some interesting lessons worth sharing that I learned in developing the tool that can apply beyond sort of these standardized assessments. They extend to, say, exams and even just homework questions, and then part research story. So I'll thank you in advance for bearing with me. I think I've got a coherent story together, but it's maybe a little wandering. So this problem started, like I mentioned, when I started my postdoc. I got involved in teaching first year undergrad labs sort of right away when I was with 17 and 18-year-old students, and it struck me, wow, these a lot of these students do not know how to think about data, how to handle data. And when I spoke with faculty, who of course had a lot more experience teaching at this level than I did, they sort of said, "Yeah, duh, we knew that this is a tough skill, and yeah, the students really struggle with it." So we hadn't collected any data at this point, but it was obvious that this was um, a problem. So I started looking at the the syllabus for the lab course that I was teaching, talking to other profs about the syllabi that they had, and didn't ever see, and I'm just speaking for UBC at this time, didn't really see indications ever that these were skills that we were explicitly teaching. It was just sort of thought, we'll give them some formulas. I don't know if by osmosis they'll practice this enough, they'll get the hang of it, and by the end of a degree, they'll know how to handle data. And I wasn't sure if that was true or not, but it was clear to me here, at least at UBC, that we weren't teaching these skills directly. Um, and so I did spend a little bit of time thumbing through the literature, and this is maybe probably not news to anyone here, but I learned that other folks have thought about this and looked into it, and it's pretty easy to conclude and fair to state that unless you're targeting these skills pretty directly, with learning goals in mind, um, you can't really expect your students to develop these sorts of skills. And that meant, again, at UBC, I saw that there was a bit of this hidden curriculum problem. Um, we assume they'll pick it up. Uh, Students in these fourth year labs should have it because they're at the end of the degree and they probably learned it in third year. But students in the third year labs, they were taught this stuff in second year. And in the second year labs, they must have covered it in the first year labs. And I'm in the first year labs. So I'm like, we're not covering it. Like, so where are the students getting it? Um, so this became a bit of a motivation for me. Students are clearly missing these skills. As a maturing scientist, I felt it was important that we help students develop these skills. And if you're going to do that, you're going to have to somehow measure whether or not they have these skills. Now, the motivation was one great thing, but we also had this nice little, I had some impulse. So just the year before I'd started my postdoc, Carl Wyman had been lured away from Boulder, Colorado, and he came to UBC to set up what they called the Carl Wyman Science Education Initiative. And so he was a big cheerleader of this idea. He's like, this is something that's the sort of tool is missing. You could think of developing something like this. And there's plenty of ideas that he had that we had for how we might then use this tool to do some research with it if we so chose. Um, Beyond that, I didn't just have him as a great cheerleader. He had a graduate student who was finishing up her degree, Wendy Adams. And Wendy was, for her thesis, she essentially was figuring out the best practices for developing and validating these sorts of assessments where you can measure expert-like thinking. And so, again, I didn't just have a cheerleader. I had Carl and Wendy who were going through this thesis and then eventually writing this paper, who knew the best practices. So they could give me a bit of hand holding and make sure that I did this the right way. So if you're not familiar with their paper, I'll share with you a little bit their framework. They've got a sort of a three-stage framework. The first stage falling under the umbrella term of cognition, and this is defining what the students are supposed to know or be able to do. So identifying the thinking, the reasoning, or the skills that you want to measure. And this is the first step of the foundation, and everything else depends on this. So the second part of their framework, observation. So this is designing the tasks that would reveal their thinking. So whether it's an assessment tool or a final exam, your items, your questions on there have to be opportunities for students to show their reasoning in action. So like if cognition is the blueprint, observation here would be like the construction. You design tasks that allow students cognitive processes to surface so that you have a chance to actually see them. And then interpretation is making sure that the scoring or the analysis of your assessments here lead to valid conclusions. The evidence that the students generate should support the inferences that you want to make. And so it's the third but equally critical component of this framework. So in brief, the cognition defines what you want to measure. The observation will how you will elicit evidence of it. And then the interpretation is defining how you'll determine what that evidence actually means. And so each step constrains the next. And if you follow this carefully, you can build a valid and reliable and meaningful assessment. Um, so before you even get to the first step, I sort of mentioned this. I mentioned learning goals earlier. You need to have learning goals, and the definition I would provide for learning goals are they're operational definitions of what you want a student to be able to do at the end of your class, at the end of your course, at the end of your degree, and they got to be measurable. So, but they could be as simple as like at the end of this class, my student should be able to calculate a standard deviation and explain why it has the form that it does, or something like that. Um, so learning goals are step number 0. Once you have those, you have a chance at crafting questions that get at the things you care about. You should be starting with the learning goals and then writing questions where there's a clear tie back to the learning goal you had in mind. If you've got questions on an assessment, whether it's homework or a final exam or a tool like this, if you can't draw a straight line connecting it back to one of the learning goals you said you've cared about, I would suggest maybe that is not a question you need to be asking. And so for this assessment development, we started with open-ended questions and we had students complete them. We will interview the students to talk about their solutions. We might have them talk aloud as they're generating their solutions. And when you have all that information, you have a hope of crafting some multiple choice versions of the same sort of questions. And then again, there's interviews that might be involved with the multiple choice answers that students give. And multiple choice is just, it's a great format because it's easier to score in bulk and things like that. But once you've got a bunch of questions, interviews were our next steps. And I mentioned this sort of think aloud technique, and this is something we applied at multiple stages of question generation. So early on, it might be getting students to sit down and come up with solutions to the questions that you've generated because of your learning goals and that you think might make a great assessment item. And then after they've done it, you ask them to explain their reasoning, why they did what they did, and how they got to the answer. Uh, Alternatively, you might just ask a student, do your best to say everything that's going on in your head while you're coming up with your solution. Don't worry about complete sentences. This is just like, this is out loud train of thought. Okay, whatever they're thinking, you just want to hear it. And you can learn some surprising things about how the students are thinking that aren't obvious just based on what they've written, or especially by the time you've gotten to multiple choice, all you might know is the option they've selected. So you can learn a lot by going back and asking them, how did you get to select option B for this question? A couple of examples of answers that students might give where the think alouds really highlight what a problem might be. So we had a version of a question where we wanted to see whether students could calculate a weighted average. And the question involved something like giving them a couple of data points with different uncertainties. So for example, 90 plus or minus 8 and 100 plus or minus 2. And they need to take those two data points, combine them together somehow, and then use that in a subsequent simple calculation, and then from that they'd select an answer. And in one of these interviews, we found that students were sometimes getting the right answer for the wrong reason. So instead of properly calculating a weighted average, we found a couple of students would say, oh, 90 plus 8, that's 98, and 100 minus 2, that's 98. That must be the right number that I'm then going to use for my calculation. They do it, and they'd get an answer that didn't appear on the 4 or 5 options they were given, but the answer that it was closest to was the answer that an expert would get if you did a properly calculated weighted average. So students were getting the right answer for the wrong reason. So this was a question we had to tweak, and we never would have known this without talking to enough students to elicit this incorrect reasoning. As another example, we had early on some questions where students were presented with data points on a graph and multiple potential lines of best fit. And in talking with a number of students, getting them to talk out loud as they were going through this, we noticed that some students that were not seeing all of the data points that were on the graph. Our little symbols were small enough that some of the students assumed that it was just like a photocopy or smudge. So they were getting the wrong answer, but that's because they weren't even understanding the question properly. So they had the wrong answer for the wrong reasoning. Um, and again, without these sorts of interviews or think aloud conversations, I don't think there's any way we would have known that questions were performing improperly for these reasons. So a bunch of misconceptions were uncovered, that the source of them, and those sorts of things actually can help us shape the distractors. And by distractors, I just mean the wrong answers that look convincingly correct to the students. And so again, whether you want to go through the larger effort of creating an assessment tool, or you're just making next year's final exam or next week's homework problem set, it's always a good idea to talk to the students. I think it's good practice to make that a standard part of your design. Okay, so we went through all this, and then we had a small bank of maybe a dozen or 15 questions that had a chance of, maybe making it into this assessment tool that we were working towards. And I can't remember where I came across this, if a colleague said this to me or I attended a talk that someone said this, but um, I heard these 5 words: without validity, reliability is moot. So reliability is about like hitting the same spot every time, but validity is about hitting the right spot. So if you're aiming at the wrong target, consistency doesn't help you. A perfectly consistent measurement of the wrong thing, totally useless. So before we got into determining whether or not the instrument we were creating was reliable and how it functioned, we had to ask ourselves, is there evidence that it's valid? And there's lots of different types of validity that assessment making folks talk about and care about. And you can hit a lot of them by actually just handing your assessment out to a number of experts. So we gave it to a bunch of faculty and a bunch of TAs. Face validity is actually it's like a first superficial subjective check. Does the assessment seem to measure what you're claiming it's measuring? So if I have a math assessment and you thumb through it and you're like, yep, these are math questions, that's kind of face validity. Content validity is more rigorous, expert-based assessment of whether the test fairly comprehensively covers the domain of what it is intended to measure. And so after a number of distributions to faculty and conversations, we got to a point where they said, okay, well, this subset of your 15 or dozen questions uh, absolutely is evidence of content validity. They helped us flag some ambiguous wordings, things that actually didn't come up with students. We had people say, I always find that any question to do with radioactive decay, I don't know why the thinking goes sideways, but it tends to. So we changed language like that, revised some items. And then I'll come back in a few slides to construct validity, but because we distributed it to a broad range of folks who are expert relative to, first-year undergrad students, there was initial evidence that we absolutely could use these questions to tell the experts from the beginners and even from the folks in between. So this expert to student performance comparison existed here. So fairly confident that this CDPA tool was hitting the right spot. In other words, it seemed to be valid. We were ready to turn to some metrics to determine whether it was reliable and actually to quantify how it functions. So the next couple of slides will show a family of metrics used to determine these sorts of things. The jargon from the test making field is psychometric properties. And we went through about a half a dozen of these. So one of the first ones we measured is what is called item difficulty. It's really just the proportion of folks who get a question correct. So if your item difficulty is 0, that means no one ever gets the question right. And if it's 1, it means everyone gets the question right. And you can probably understand that those two extremes don't help you learn anything. So the questions that we ended up keeping on the assessment were those that fell between about 0.25 and 0.8. Some questions were pretty difficult, some were relatively easy, but it covered a good range of abilities. The next psychometric property was item discrimination. That's what it's called. It really just distinguishes whether the question distinguishes a strong performer from a weak performer. And the folks who do psychometrics have a heuristic line in the sand. They suggest that your items should be above 0.3. We had an average of 0.43, only had one question that was below 0.3. So it suggested that each of the items in our assessment, which at this point was 10 questions, were strong discriminators. The next was something called point by serial correlation. It was nothing more than how an item correlates to the total on a test score. And this was actually a relatively low measure. Our point by serial correlation was about 2:1. But we weren't surprised by this because this assessment was probing more than one ability. It was probing like 3 or 4 abilities to do with data handling. And we were trying to do it in as few questions as possible. That's what the C in CDPA stands for, concise. So if you're trying to probe a small handful of things with as few questions as possible, we shouldn't expect to get a super high correlation between the item and total, but this 0.21 fell above some critical value that experts in the field say you should hit, that was about 0.125 or something like that. So that's that. Just a couple more here. Another one called the Ferguson's Delta, which is a score distribution spread. That number came out pretty high, which said at the test level, it does a very good job at discriminating the weak from the middle from the strong performers. And then as far as reliability goes, a Pearson R, a test retest thing. So how stable is this tool across administrations? And this might be giving the assessment to the same population of students, but different in time, or giving it to nominally identical populations of students at the same time. And either way, the tool always seemed to perform the same across these administrations. So we were confident that it was pretty reliable as well. And then I mentioned that I'd come back to this construct validity. So after having gone not just through the initial development, but as we're getting closer to the end, it went out to like 600 or 700 first-year students, a couple hundred students who are in second or third or fourth year, about 30 or 40 graduate students, and about a dozen faculty. And there were statistically significant differences between the scores for all of those groups. So when someone comes straight out of high school before we've taught them anything, they score about chance on this thing. And they actually often score at a little less than chance, because some of these questions are tricky and have some very convincing distractor items. By the time they've been taught the material, so at the end of first year, they're scoring just under 4 out of 10. And by the time we are looking at the fourth year students, they're scoring about 4.5 or 4.7 out of 10. Grad students were getting 5.3, which is maybe they've learned a little more, but also maybe selection effects because the best undergraduate students are the ones who continue on into grad school, maybe. And then faculty who should know a lot of these things, were getting 8 out of 10. So it was even the experts found the items on this assessment tool pretty uh, pretty tricky. So what do I want to get to next? So this is we have evidence to support that we've got a working tool. So in 2 sentences, what I would tell you this tool does and what it does not do. It does give a measure of students' ability to reason with measurements, uncertainty, and how they think about the relationships between equations, models, whether that's graphical representations or symbolic and actual data. Uh, but even though we've always deployed it in lab settings, teaching lab settings, it doesn't at all measure their proficiency with lab procedures, software tools, or any of the specific mechanics of the mathematical processing that they might have to do. So that's what the CDPA does and doesn't do. And these are two, if you haven't come across them yet, these are two references I'd like to share with you. And most of what I've talked about up until now is what's covered in this first publication from 2011. So this is really, I would say, a case study of the that Adams and Wyman publication I gave you earlier. So they sort of said generically, this is the best practices for developing and validating an assessment. And ours is like, here's a specific example of us following these great instructions, and you can get a tool that works. The second paper was my one and only attempt to see if we could address some sort of research question with this tool that we had developed. And the second paper is actually two things. So on the surface, as I just mentioned, it's an example of how the CDPA can be used to address a research question. But what I really like about this paper, my favorite part about it, is that it's a cautionary tale to the PER field of what can go wrong in your research, or more specifically with your analysis, um, if you're not careful. And it's sort of told in the form of, hey, check out all of the mistakes that I made when trying to answer this research question. And so I'll get to the next part of this talk is mostly drawing on things that we covered in the second paper here, where we're using the CDPA. But in using it, we have learned, in developing it and in using it, we've learned quite a bit. And so under the umbrella category of what we learned, fortunately, we learned that students do learn. So if you're explicit in addressing these skills, because you've crafted learning goals, and you explicitly teach them, the students can absolutely start to learn these things. That's a great thing. And over the course of our first year lab, uh, the student scores increased by about 1.5 points out of 10, which I grant isn't a lot, but I will repeat it. If you consider that these questions are rather tricky and that a lot of faculty experts top out at about 8, we're happy with this. So in 4 months, you can absolutely teach the students something. This next thing is something I mentioned, the main research conclusion from that second paper that I just shared. And this is broadly consistent with what others have found in similar studies using other concept inventories, for example. And it's that there is a gender gap that isn't eliminated by instruction. And if you're interested in reading a little more, you can check out the paper. But I'd say that this is largely because you can't separate the doing of physics with the doing of gender. This intersectionality is a thing and it matters. And as an instructor, it behooves me to never forget that this always applies. Um, okay, so I also mentioned that the second paper, what I liked about it was that I tried to make it as pedagogical in nature as I could, because even though we are following this close and careful guide for constructing our assessment tool, um, I was new to the field of PER, relatively new to the field of PER, and so I made a ton of mistakes. And I was always frustrated as a graduate student about, null results or experiments that don't work and never get published. And you talk to people and you're like, oh, I just discovered this thing doesn't work. And like, oh yeah, no, we knew that didn't work back in 1967. I just did that experiment and I didn't publish it. I put it in the file drawer. So rather than hiding my mistakes away, I wanted to share them so that others would repeat fewer of the mistakes that I had made. So the next bullet points I'll pull up here are sort of like a highlight reel of my best mistakes, if you will. Starting with what seems to be a simple first analysis. And that's trying to measure the student learning. So you may or may not be aware that there exist a lot of standard metrics out there that try to do this, and they go by names of like gain or normalized change or things like that. And the formulas for calculating all those things are, roughly speaking, they're a fraction where the numerator is often something like the post score minus the pre-score, and the denominator might be something like the maximum score they could have got, or the maximum score they could have got minus the post score they got, or something like that. But it's roughly a fraction of how well they did over how well they could have done. And I didn't know which one to pick, and so I started goofing around with all of them, assuming that there would be a few minor differences between them. But I quickly found out that when I did that, my data became a bit of a choose your own adventure story, that these different estimators um, could lead to different conclusions and sometimes even contradictory. So I wasn't sure what to make of that. So I guess I'd say the first lesson is that user beware. You need to be thoughtful when you try to quantify and make claims about how students have learned, because there are certainly examples. And then when I went in the literature, I found actually I wasn't even the first one to have noticed that depending on your choice of I'll just call it gain as an umbrella term, you could get differing and sometimes conflicting conclusions. And so not still in the early days, still not knowing how best to handle this data, I thought like, well, I've got distributions of scores. I'm aware of statistical methods that one can use to compare distributions. So I'll just start doing that. And in doing that, I actually came across this is maybe the my favorite title of a paper that I've ever seen. Are assumptions of well-known statistical techniques checked, and why not? These are folks from the field of psychology. And their study essentially revealed that researchers rarely checked assumptions for the statistical tests they were using, largely because they didn't know that some of these tests had prerequisites. Um, and even when they did, they were unsure for how to assess them. And so this led to authors concluding that statistical practices, at least in the field of psychology, were often opportunistic, prioritizing um, the output rather than the mathematical validity of the analysis. And because I was in the goofing around stage, I was like, well, I've just done that too. So what do I do? It became clear at this point that I needed to find an expert to help me with this analysis. So I fired an email off to to a faculty member at UBC in the Department of Psychology who specializes in research methods and statistics. And she said, first of all, I'll make sure you understand how to use these tests, which assumptions need to be met before you can use it to draw valid conclusions, how to test those assumptions and all of that. But then she also said, you also need to control for your covariates here. Otherwise, any sort of measure of raw post-test differences could be confusing or overstated, or according to some, perhaps even incorrect, which is, a shout back maybe to this first point that I have up here, where I was getting confusing answers depending on which measure of gain I was choosing to use. So in short, she told me to use an ANCOVA, an analysis of covariance, um, which helps sort out a lot of things. It allows you to make a fair comparison of the post-test performance because it accounts for pre-test differences. And that separates instructional effects from initial ability. Uh, because I remember wondering early on, well, if a student gets 5 on the pretest and 6 on the post-test out of 10, and another student gets 6 on the pretest and 7 out of post-test on the 10, they both went up by 1, but one went up by 20% and the other only by 16%. But the other one also finished with a higher post-test score. Like it was difficult for me to really understand how to make sense of that. And so that the ANCOVA can help that out. And regression toward the mean effects, when students don't know anything, if they have a good and lucky guessing day, we found some students who on the pretest were getting like 7 out of 10 and then only 4 out of 10 on the post-test. So did we do any harm? Or is this just a regression to the mean sort of thing? And then COVA can help take care of that. So that was another important lesson we learned. So a couple of big takeaways when it comes to the analysis is that the choices you make absolutely matter. And just as they did in the instrument design as I went through, but these choices matter. So I'm always reminding myself of this, that I have to be thoughtful about the analysis decisions I make. I can't just do something one way because that's how it's been done in the past, and so on. Uh, so if anyone is interested in using the CDPA, it's at the end of that first paper that I referenced. It is also up on Fizzport, and I mentioned I haven't actually thought about it in about 10 years since this last study was done. So I went to Fizzport to check it out and was happy to see that they've given it a gold star validation. That all the work we went through allowed them to check off. They've got 7 boxes for what makes a gold star validated research assessment tool, and the CDPA meets all of those. So we considered student thinking. Those are the learning goals. We've done interviews. We did the expert reviews. Uh, Thanks to my mistakes and then conversations with a professional statistician, we've done appropriate statistical analyses. I'll get to it in a second, but part of the construct and cross-cultural validity, we did run this at another institution. Other research groups have used it, and it eventually made it through peer review and is out there. So you can find it on Fizzport if you are a Fizzport user. So how have others used the CDPA? So I just mentioned this. We had a friendly colleague at the University of Edinburgh, a few colleagues, and they were serendipitously interested in these same sorts of things at the same time. So they were perfectly open and willing to run our assessment tool with their students. We sort of did the same for them, and they ran it through a big cohort of 250 students, and we saw the same sort of numbers falling out. Their pretest scores were effectively the same as ours. Post-test scores were coming out the same. And so we've got this consistent pretest conformance, not just across a Canadian system, but this UK system as well. And then, so this is the next couple of slides are what were completely new to me. Because I hadn't thought about it in so long. I actually have no idea how anyone else might have been using the CDPA in the last decade, or if anyone else had been using it at all. All of my all of the work I've done in PER here at UBC has really just been as a support guide. We have a small PER research program, and actually the faculty member who led it just recently retired. But he always had one or two students doing this kind of stuff, and my involvement in this kind of field was always just supporting whatever it was that they were doing. And they were never doing anything with this assessment, so I wandered off into other things. So in putting these slides together, I checked out how other folks have used it and was delighted to find that other folks have started using it. So some researchers at McGill just recently published a study that they did over 5 years and over 2,000 students for a longitudinal curriculum review, mapping skill progression across the entirety of an undergraduate degree. Cornell labs have been using it for similar equity reasons, like the gender gap stuff that I mentioned, in comparing and contrasting how students do in traditional labs versus ones that they have transformed. At Nebraska Omaha, they use it for accreditation purposes. So they've actually formally adopted the CDPA as a metric for their student learning outcome number 3, which they call experimental proficiency. Chapel Hill has a big program called Scale Up. I forget exactly what that acronym is, but the AL is active learning. And so they've used this assessment to compare gains that students get in these interactive studio labs versus other ones. And then some folks in Italy have been doing it for some technology integration as well. So that's some examples of how others have been using it. So getting near the end and just wrapping up here. Uh, I I wondered how I would describe how this assessment tool fits in the sort of the assessment ecosystem. There's no doubt it's niche. There are not many, although there are a few more now that the CDPA has come out there that deal with experimental numeracy. A key feature of the CDPA is its brevity. It is only 10 questions, so you can deploy it as a pretest or a post-test in your labs or your classes without taking up too much time. Based on how we've used it and how a few other folks have used it, I think it can play a significant role from, gender equity and technical skills to mapping skill progression over an entire degree. And then a reminder, I want to call back to this paper because it was so integral in developing it. It's the CDPA is one of, if not the first sort of case study in how to build an assessment properly. Um, sort of to finish if you are going to forget a lot of what I told you, the couple of things I'd like you to walk away with, to remember. Um, I think good assessment starts with clear learning goals and a sufficiently rigorous development process. It probably shouldn't start with writing questions first. The questions should come after you know what it is you want your students to be able to do. Validity and responsible data analysis matter just as much as the instrument itself. I floundered for a couple of years, making all sorts of mistakes. And so if one is thoughtful about it, you can make fewer mistakes than I did. And tools like the CDPA reveal that data reasoning skills they're definitely difficult to teach. And I think they're still probably under taught, but with enough effort, we can absolutely design better labs and assessments when we make these skills explicit. And that's all I wanted to tell you. I hope I've left enough time for questions, conversations, feedback, whatever. Thanks for your attention.
Great. Thanks, James. Um, Kareem had a question early on regarding
Okay.
AI. Do you want to elaborate, Kareem?
Oh, sorry. Yes. Yeah. So my question, or not really a question, but more like a concern, when you were talking at that moment about asking students to do a weighted average, and I'm thinking about all these different operations, but those have become so easy to do now with AI, even with very minimal understanding of statistics or statistical procedure. Almost any student could just type a short prompt and come up with a pretty good answer. how does that fit into this outlook of trying to test those skills with a CDPA here?
Yeah, that's a good question and a great concern. When back when I was doing this, AI wasn't the thing that we thought about or cared about at all. And even though I haven't thought about the CDPA very much until recently, the whole idea of how we deal with AI without, I mean, it seems clear to me like AI is not only is it coming, AI is here. So I think that we've got responsibilities to make sure that students use it responsibility. I don't belong in the camp that we should say no AI ever at any time. But I think it's important to get students and people to think about how to use it properly and responsibly. Um, and so for at least in the moment that uh, a student or a class might be answering the questions on the CDPA. So we've always done it like paper and pencil in class with whatever devices down. So in the moment, there wouldn't be any reason to worry about students short-circuiting their learning or cheating or whatever in answering these questions. But I'm gathering that your bigger concern is how they might be self short-circuiting when they're actually having to do this in the wild. Am I understanding that correctly, Kareem?
Yeah, because I'm not too worried about the cheating part. I'm more concerned about whether does it make sense, for instance, to even expect them to know how to do it by hand when, in practice, if they ever need to do any kind of statistical calculation, they're most likely going to go to AI and just type a prompt, even if they never took a class in statistics in their life. And so, is that a skill we need to teach? I mean, maybe not for physics majors, but for the general population of students, how much
So,
do they need to have?
um, but so maybe that conversation begins by asking ourselves whether we can convince students or the general population that this is a skill worth having. I mean, just because you can get AI or a computer to do something for you doesn't mean that
Mm.
therefore we don't need to have it. One thing about uh, many of the questions on the CDPA is you actually don't really need to do a lot of math. Experts don't need to do a lot of math to get the right answer. So, given uh, given a couple of data points, an expert probably wouldn't calculate a properly weighted average. An expert might say data point A is clearly better than data point B. I'm just going to roll with that one and ignore it, and then they can do the simple calculation that follows without having to calculate a weighted average. Uh, things with experts know pretty routinely, for example, when they look at like the underlying functions when if they see a straight line, for example, on a log-log plot versus a log-lin plot, they don't need to they don't need to reverse engineer the math out of the line of best fit to realize, oh, this is an exponential I'm looking at. They can just look at the axes and be like, oh, this is something that's tripling every time unit or something like that. And uh, And so I think, I mean, I can imagine why these sorts of skills might be important to the general public, even if it just means they're a little more skeptical and cautious of how some journaling or writing is done. So, like I know um, a common example that I've noticed among students or people who haven't yet developed the skill, if they see something is changing quickly, it's an exponential, according to them, right?
Yes.
So, uh, but exponential means something, and they don't need to know what it means as well as an expert like you or I might mean it, but they, I think it's important that they, for example, when they read the word exponential, they stop and pause and wonder like, is this is this truly exponential, or does this journalist really just mean it's increasing a little faster than linear? And it looks big to me. So I think uh, I think there's ways we can convince students and the general public that that having a handle on these sorts of data reasoning skills will make them better citizens. Um, Even if you then have to, like, fine, if you have to grab your calculator or paper and pencil to calculate a weighted average, that's fine. I would just love it if students know that not all data are, I mean, you shouldn't be creating data, but not all data are created equally, right? Like there's a difference between seeing a data point with big error bars versus little error bars. And
Mm.
if students even know to ask the question, are those standard deviations or confidence intervals or uncertainties in the mean? Like to just to know to ask the question, okay, uncertainty belongs to this measurement, but even what is this uncertainty? I think that's a win. And it's not um I hadn't thought about the AI question until you've raised it, but as I'm talking through this, it's not obvious to me that at least yet that's something that AI could immediately help them with. I don't know. What do you think of that,
Well,
Craig?
my very brief experience with this is that for a number of years I've been asking students to do some t-tests when they do some data collection, like comparing two balls or that sort of thing. And so I was, because it's a introductory course, I was using an online resource that only asked
Mhm.
them to provide the numbers, the average, and then the standard deviation, and they would do the calculation of the p-value for them. And then based on whatever they get, they can make a claim as to whether there's a meaningful or not meaningful distinction between the two averages. And then one semester that didn't work. And so I thought about what could we do? And I was caught by surprise. I didn't have time to really plan much when I found out that the site didn't work very well. So I told them, why don't we just use AI? It was, I think it was a year and a half ago. And so they just went online and I asked them to actually told them to do that and said, okay, here's my data. Give me the p-value for this. And they didn't really need to do much. And in like 1 second, they had the answer. Okay, for this data set, here's the actual p-value. And I checked later that it was actually well done. I mean, there was, I think, ChatGPT. And actually, they used multiple AIs, and all of
Okay.
them were giving them pretty good answers. So then I'm thinking, okay, so from now on, should I direct them directly to AI and then use whatever they get for some other purposes? Maybe I'm still thinking about what I need to do here. But whether having to explain to them well, of course I would have to, but I usually shortcut the discussion because it's not a statistics class, so the p-value and all those things. I just try to tell them what to do with the difference between two averages, and not just simply tell me, oh, these things are different, and that's the end of it. But it looks like the AI may be opening different options at this stage, which I haven't completely thought of yet.
Yeah, it's opening a Pandora's box of options, I think.
Yeah. Um, I don't know. The question just came across my mind, but I don't have a really strong opinion yet on what to do with
Yeah.
that. But at the same time, we've been developing what we refer to as general education learning outcomes in our courses. And
Hmm.
all of them are structured in the form of sort of data analysis, what to do with analyzing data and recognizing developing what we call a scientific reasoning process. And so I think what you just described might be very useful in trying to quantify what you're trying to do in a more qualitative way in sort of sense. So now I'm thinking that's going to be very helpful. Try to share that with my colleagues.
Yeah. Yeah, share it. And if you, I mean, for anyone here, please don't hesitate to get back in touch with me if you want to talk more offline or whatever. I love thinking about this again now that it's been a decade, and even if you just need a wall to bounce ideas off of, I
Okay.
would love to do that with you.
Okay, great. Thanks.
Any other questions or thoughts?
Charles has a question.
Oh,
Um,
fantastic.
so I'm looking at the paper referenced, the original paper. I wanted to take a look at the learning goals that you had, and one of them mentions extract meaning from the slope and intercept of data which have been linearized. One of the thing, and I was curious if when you folks were looking at that learning goal, whether you meant the mathematical meaning or tying it to some underlying physical model of some sort of process. In other words, how far back did you want to take the actual uh, learn goals in terms of generic math stuff or tie back to physical parameters?
Okay, yeah. So I'm reaching way back in my memory for this, and uh, my memory is that the instructors were mostly concerned, I think, with linearized, mostly concerned with primarily with, for example, making a log lin or a log log plot just so that exponential or power law behavior appeared linear. Um, More so than anything else, but I it's been long enough that I'm not sure I can answer that question with much confidence. And I don't actually I didn't look back at all of the learning goals we used to have. It might have been that that was like a header learning goal, and there might have been specific sub-learning goals underneath that covered those other categories.
Thank you.
Yeah.
Thank you. I think at this point, we'll stop the recording. We can stick around for more discussions afterwards. But thank you again, James.
Thank you.